And today we're coming together to look at the future. So while a lot of tech stacks are beginning to implement parallelization and sharding to solve their scaling woes, Gavin Wood, who is the author of the Ethereum Yellow Paper and the founder of Polkadot, has been developing the Jam Gray Paper to marry the performance of Polkadot with the coherence of Ethereum mainnet. And this future, this beautiful future, may be a lot closer than we think, as we're going to see today on stage, starting with our first speaker, Kian, who's working with GrayMatter, a team looking to implement the Jam Gray Paper. Let's welcome Kian to the stage.
So, thank you. I think Jay's intro was interesting in that, in some sense, it seems like where the blockchain space and sharding is going overall, it's like a movie that we've seen the end of it and we're going to the next stage, while the rest of the ecosystem is going to where Polkadot was like a year or two ago. Okay, that's some thought for the future. For this talk, I'm going to be giving a presentation that's called Demystifying Jam. This is the condensed version of a blog post that I published a few months ago, with some alterations and some modifications. I hope with this presentation for the rest of today, we will all have like an equal understanding of Jam and can then listen in a more attentive way to the rest of the talks that we have today. So it's a very like beginner-friendly introduction to what Jam is. So I'd like to start this talk with naming a few things that I think Polkadot has done so far in a very novel way, and then focus on one of them. There's some social stuff in there as well. I think what Polkadot does in OpenGov and Fellowship, declaring the DOT token, or sort of saying that it's coming to this agreement with SEC that it's a security, all of these I think are non-technological novelties of Polkadot. And I think in some ways they are novel and unique within the Web3 space. As someone who has contributed to Polkadot a small bit, I actually feel quite proud that we are experimenting with these things. And if I look at the technological front of Polkadot and say what I think is the main advancement, is this long statement that I have here, that we have managed to deliver heterogeneous execution sharding with shared security. I mean, it's a mouthful, but I will decompose this phrase going forward. So let's look at this phrase, execution sharding with shared security, and see what it means one by one. Let's first talk about sharding. So this is what blockchains wanted to do for a long time. If we look at like the Ethereum articles and blog posts from 2017, 18, 19, it was all about this concept, execution sharding. Ethereum wanted to become a blockchain that has 64 shards, and they would all execute EVM contracts, and they would all come to some kind of settlement on a base layer. That being said, the roadmap of Ethereum itself have pivoted a little bit from this execution sharding. So in order to understand how this execution sharding will work or intends to work, let's first start with what is a non-sharded blockchain. So I call this a sequential blockchain. So we have the blockchain as an entity. We have all of our validators. Blocks come in sequentially. Every block that gets processed has to be processed by all validators. So there's a lot of coordination involved. If one block wants to come in, everyone has to re-execute it. And this premise is the underlying, or this assumption is the underlying reason why scaling blockchains has been so difficult so far. Because our assumption is that any block, any bundle of transactions that comes in, has to be executed by all validators. So this is a classic blockchain. And how, if you look at just the Polkadot relay chain, this is how it works. If you look at just the Ethereum L1, this is how it works. In fact, if you look at Solana, this is also how it works. They have just optimized the max out of it. So the naive way to then say, okay, I want to shard this, is to look at this and say, I have this big block of validators. How about I split them into 2 parts or 4 parts? And now I can have 4 times throughput. Great, right? So it would look like something like this. I would call this poorly execution sharded, in that yes, we have sharded our execution, but we have also sharded our validator set. And as you know, The validator set is what brings security to the blockchain. The amount of stake backing a validator set in a proof-of-stake network is what we call the economic security of the network, and it's what is the source of security. So if we split this into 2 parts or 4 parts, we're also dividing the security of that blockchain into 2 or 4 parts. So this approach brings scaling, or it shards the execution, but it also shards the economic security. This is more or less the original Cosmos model, and I think it's something that overall everyone has moved on from, as in we have acknowledged that it's, it's not a very elegant way to scale. And really, if I want to boil down the main novelty of Polkadot and in the technological level, is cracking this equation, solving this problem such that we can have execution sharding, but there is no longer this fragmentation of security. So it looks more like this, in that you can see now these blocks that are underneath the validators, they don't have different colors. They all have the same color of the Polkadot itself, and through this visualization, I'm trying to imply that we are sharing the security of Polkadot. So how this is achieved, it's beyond the scope of this talk. You can imagine it's through some game theoretic games that validators have to play with one another. They have to check each other's work. This is formalized, I'm very glad to see, finally in a paper called Elves. It's published this year from Web3 Foundation. And the term that we use for it is cynical rollups. So it's very much, it is in some ways similar to optimistic rollups, but it's more proactive in how different groups of validators check each other's work, and therefore we call it cynical rollups. But TLDR, what it brings about is this 2 properties that so far we thought they're mutually exclusive, but we actually realized we can have both. We can have sharded execution with shared security. And within the context of Polkadot, when we split our validator groups into these smaller groups and we let them work in coordination, but the security of this smaller validator group is still very high and as high as all validators, we call them cores. This is very important. So this is like a Polkadot specific terminology that we're going to be using for the rest of this talk. One other detail from up until this point in this presentation, this diagram, is that also for now you can see these shards, they are all of gray color. They are all of the same color. So it's a homogeneous sharded system. So this is, for example, like the vision of Ethereum 2.0, that you have 3 shards, but they are all the same thing. Those 3 shards are the same blockchain. It's just more throughput of the same thing. And finally, Polkadot took this a step further, and with the clever use of WebAssembly to represent a shard, it introduced what is the final component of that sentence that I'm decomposing here, heterogeneous. So it made this sharded system with shared security also heterogeneous. Now each of those shards can be a different blockchain, right? So one of them can be, I don't know, Moonbeam, Bitcoin, Ethereum, hypothetically. So this is already beyond, for example, the original ETH 2.0 vision. And this is more or less what Polkadot 1.0 was. So what I want to emphasize here is, again, this technological achievement of sharded execution with shared security in a heterogeneous manner through introducing this concept called cores, which is a group of validators working in coordination. And so the last diagram was Polkadot 1.0, so that's like mid-2021 or end of 2021, whenever Parachains got launched at first. And if you look at the evolution of Polkadot so far, so in the last 2 years, it's really all about making the usage of cores more flexible. So it's an acknowledgement that, hey, these cores are awesome. It's actually like something that no other tech stack out there, no other blockchain ecosystem out there has been able to achieve. And let's make them easier to use, more flexible to use, more readily available to everyone. So I have many examples of that here. If you want to get more out of the single core you have, this is async backing. These are like code word for features that have been released in the last 2 years. Depending on how familiar you are, you might know about them. if you want multiple cores, then we have elastic scaling, the ability for one parachain to use multiple cores and get even more throughput in. If you don't want to commit to a long period of time for how long you want to use your core, then we have agile core time. If you want to commit to not even any duration of time and just use a Polkadot core on demand, then we have on-demand core time. And finally, I can squeeze in that if you want to use this core for a non-parachain usage, that's one of the areas where Jam comes in. That's where Jam is the answer. But really the overarching conclusion here is that really Polkadot's main technological achievement has been the introduction of these execution cores that have very, very powerful properties. And then the rest of the evolution of Polkadot has been all about, okay, how can we make these cores, useful to the widest audience possible? Okay, one last thing that we need to go over before we dive into Jam is to look at what happens in a parachain block when it's being processed by Polkadot, and then this will help us understand Jam better. So path of a parachain block. So first step, this purple box is the block that wants to be processed, and we are focusing on the middle core, which is going to process it. And again, these cores are a group of validators that are working with coordination. So if Polkadot has 1,000 validators, each core is like 5, 10, a smaller subset of validators. So first step is that this block will be sent to this core, and this core will perform computation on it. In a few diagrams, I use this what is this? It's like this wheel or gear symbol to represent computation. So this is where the bulk of the computation of processing this block happens. Not by all Polkadot validators, but rather by this smaller subset in the core. Once this is done, to fulfill the security guarantees that ELVS requires us, it's not like this small group of validators does the work and we're done. We have to then create a system such that we can be sure that the data needed to re-execute this block by other validators, should they want to do it, is available. And this is where the data availability system of Polkadot comes in. So as the next step, there is a data availability layer in Polkadot already, and this core that executes the block will propagate this block and the information needed to re-execute it through this data availability layer, such that other cores, other validators, if they want to recheck anything, they have access to the information. And finally, what happens by all Polkadot validators, what all Polkadot validators do, is not re-executing this whole parachain block, is in fact just updating a small signature of what was the outcome of this. So in the case of a parachain, this just means updating the state root of that parachain, for example. So one hash gets updated on the Polkadot state, and this is executed by all Polkadot validators, but that's it. No more work is being done. So this is my story of path of a parachain block. But what I want to get out of it is this very interesting dualism that is 100% unique to Polkadot's architecture, which I would call in-core on-chain dualism. In that, as a parachain block is being processed, it's going through two different phases that have different properties. At some point, it is inside a core, so it's being processed by some validators, and this is where most of the computation happens. And at some point, it's on-chain. And by on-chain, I mean all validators are executing it. So inside the core, we do the actual execution of that block. We also make the data available to everyone else. And on the chain, we actually do a small signature update. So within this dualism, you're also seeing that in-core is where we do a lot of computation. We have more bandwidth. We are more free to do whatever we want. Whereas on-chain is where things are super secure, but also it's slower. So we better do less work on-chain. Again, if I want to go on a small sidetrack, when there's conversation of what is block space, what is core time, it's a bit complicated how to describe these things in the Polkadot world, but I think on some level, if you want to be accurate, we actually have to reside on these custom keywords, because Polkadot's block space is not similar to other blockchains at all. Other blockchains just have one type of block space, and it's just the on-chain one. Whereas Polkadot has two very different types. You know, it's like if you want to have a technical conversation, you need more keywords to describe them. So anyways, within Polkadot, we already have this in-core and on-chain dualism. Moreover, as I talked about, we already have data availability. And this data availability layer is used to keep the evidence to re-execute whatever happens on a core in the future. So if everything that I have said so far is comprehensible, I can say at an architectural level, you already know Jam. You already know everything that Jam is. And why is that? Because I can describe Jam on some level, at an architectural level, as a gutting of Polkadot. So we are kind of exposing the internals of Polkadot, such that what happens in core and what happens on chain and what you put into the data availability or read back from it is up to you. It's no longer defined for you. It's no longer hard-coded. As a programmer who programs, we call them services, in Jam, you can write the code of what happens in core on chain and what you do with your data availability. If I want to draw a comparison, a parachain on Polkadot can actually dictate what happens in core. You know, it's whatever the parachain block is doing. But it cannot really control what happens on chain. What happens on chain is fixed. Polkadot decided that for you. What happens on chain for a parachain is just this updating state root and a few other hashes and so on. Or what is put into the data availability layer is not up to the parachain. Whereas in Jam, these things become configurable, become exposed to developers. So this is the main sort of definition of what Jam is. Beyond that, what Jam does is also removing a lot of opinions from the Polkadot Parachain protocol, such that it's no longer a very blockchain-centric protocol. So you can use services to do computations that are beyond blockchains and more resembling normal softwares. We see examples of this in a few minutes. And finally, with this, I can sort of conclude that Jam is an evolution of not Polkadot as an ecosystem or as a whole, but rather it's an evolution of the Polkadot relay chain, specifically parts of the relay chain that handles parachains. So that being said, it's not a replacement or a sort of it doesn't affect things like the existence of parachains, the governance system, the staking system, the existence of Asset Hub and the DOT token. Everything remains intact. It's mainly an upgrade for the Polkadot's relay chain and the Parachain protocol, or the Parachain protocol part of the relay chain, to be specific. So it's also important to emphasize what Jam is not. So it's not like a drop-in disruptive update to everything Polkadot related. It's really an update for a low-level protocol part of Polkadot. So let's talk a little bit more about what I mean by removing opinions. So Jam is programmable by a primitive called a service. A service is represented by a PVM bytecode. We have a talk about PVM, I think, later today by Cyril, so he will go into more details of that. A invocation or an instantiation of a service. So when you want to sort of trigger a service, it's called a work item. And a group of work items are called a work package. Now, I don't mean to give you random terminology here. The reason I bring these up is to emphasize how unopinionated the protocol at the specification level is. So it's no longer a smart contract or a block. It's just called a service. And similarly, the word work item, I think it's like the most ambiguous term that you can think of, but it's also because Jam doesn't want to dictate what these work items are. It wants to be general. Then, to see how this in-core on-chain dualism plays out in Jam, we can look at what a service is. So a service, hopefully in a very intuitive manner you can now understand it, it's just 3 entry points, and 2 of those entry points are very self-explanatory. Refine and accumulate. So refine is what happens inside the core, accumulate is called what happens on the chain. Now the names are, it's not just called FN in core or FN on chain for reasons beyond this talk, but it's a very accurate simplification to say, refine is just what's happening inside the core, accumulate is just what's happening on the chain. So my initial statement, my initial promise that, hey, jam is just it's similar to the Polkadot Parachain protocol, but you have full control over what you're doing in core and what you're doing on chain. You can exactly see it here, because you have access now to this refine and especially the accumulate function, which is not really programmable in the current Polkadot model. And there's a third entry point that I don't really go into too much details of it here on transfer, which is when services want to send messages and tokens to one another. A little bit more detail about what refine and accumulate is. So first, refine. Again, refine is what's happening inside a core. And what is the property of in-core? Gas is abundant, computation is abundant, because you're not imposing this computation on all validators, you're just imposing it on one core validator, it's much smaller. So you have an abundance of gas to do computation inside your core and therefore in the refine function. Within refine, you have access to the data availability layer. You can read from it, you can write from it. Whatever you put there will become eventually available also to other cores. Although, bear in mind, in refined, you are within one core, so you don't have access to the overall jam state. That's something that you can only access in accumulate when all validators are executing things. So in some sense, you have this refine function that is like where you can do a lot of computation, and you just put the output of that computation into accumulate, which we see next. And if you think about it, the Parachain protocol is really just doing the same. Like within the core, the actual Parachain block is executed, and this state root update, or a few root updates, which are like the final outcomes of it, happen in accumulate by all validators. So accumulate is in some sense the counter, the other side of the coin for refine. So you do have direct access to the overall jam state. So it's stateful. It's less gas. You have less gas to consume in accumulate because all validators now have to execute this. So it's a little bit more constrained. And it's in a fully synchronous environment because you're no longer like, within one core of the jam chain. All validators are executing this. So all of the work items that are being accumulated at that time, you are synchronously being executed with them. If you want to communicate or whatever communication goes on between them happens synchronously. But yeah, so next I have an example, but finally as a recap, again, jam, in the most simplest term, if I want to put to word what jam is, it's these few statements. It's allowing Polkadot cores to be configured and programmed such that what happens in core, what happens on chain, and what you do with your data availability layer is up to you. So now let's look at a path of a jam work package. And hopefully it would be very similar to the path of the Parachain block that we already looked at, with just a few alterations. So I would pause here for a second for you to look at the diagram and kind of ingest the coloring and so on. So the dark gray at the top is what's happening on chain. So here we have the overall jam state and the accumulation phase, which has access to this state and can, synchronously read and write from it. That upper part is like a traditional blockchain. It's like the sequential part. At the bottom, we have the in-core part. So this is where we have many cores. In Jam, we actually have 300 something cores. And these cores have access to this data availability layer. And you can see in the diagram they are connected together, but this, I'm trying to imply here that what one core puts on the data availability layer maybe not immediately, but eventually becomes available to all the other cores. Because this data has to be propagated around. It's not like one synchronous massive database like the state at the top. Okay, and we have the work packages at the bottom. I'm color coding them to specify to which service they belong. And very similar to the Parachain model, the first step in this path of a work package is that these work packages get ingested by the cores. So they get sent to cores. And in this case, in this phase of our execution, we are doing things in parallel. And this is why Jam can do so much computation, because it has all these cores, and all of these cores can do a lot of work in parallel. And again, we have the gear symbol to represent that this is where the computation is happening. I'm also specifying there that this is the refine phase of the computation. There's also some little packets being sent to the data availability layer, if you can see. So in this phase, work items can communicate with the DA layer. So what happens next is that once these cores are done, they just put some attestation on the overall Jam state about each work package with two properties. So the letter G is representing guarantee, meaning that this work package was executed. I'm kind of using the gray paper terminology here, but I'm not going into all the details of it. So at this point, all of the three work packages have this G property checked because they have all been executed by a core. So some groups of validators have signed that I have executed this and I think it looks good to me. The A is about availability. So what is not settled yet is whether these work packages are meeting the availability criteria. And this is something that we have to wait a little bit for it. Now, this little bit kind of depends on the network conditions. It might be the next block, it might be in a few blocks. But at some point in the future, these work packages, either one of them or two of them or all three of them, they also become available. And that's the point where Jam can actually accumulate them and integrate them, and this is the final phase of the execution. So in my example, I'm just assuming that only the first two work packages are becoming available at some point in the future. And finally, we go into the phase of accumulate, where these two work packages are being executed. Again, there is this gear icon here, so there is execution going on, but it's way less because we are only running the accumulate function of these services at this point. And we have, in this phase, this transfer method, an on-transfer hook, where services can pass messages between one another. So really, I think looking at this example, it's more or less the same as the Polkadot path of a parachain, but it's more configurable, it's more programmable. So this is a diagram from the blog post. I think it's just all of these diagrams all in one. I'll wait here for a few seconds, and then I'll go to the next section. Okay, a few miscellaneous notes about other aspects of Jam. So PVM is an important part of Jam, and a lot of the sort of novelties are due to PVM. And I want to just highlight a few properties of PVM. One, that it's metered. So if you're a Substrate developer, I think there's this collective trauma of doing benchmarking and dealing with the fact that WebAssembly is not metered. PVM is metered. So this is also why throughout this presentation I used the keyword gas again. So in Jam we're going to have gas again, and PVM is metered. It's doing metering at a very good rate, as with little compromise. Actually, this morning I had some doubts whether this number is accurate or not. We can double check. But I think it's running at 50% native x86 speed while doing metering, which for a VM is a very, very good number. PVM instances can invoke child PVM, so we can have things like a service, which is itself a PVM blob, invoke a parachain, which is itself a PVM blob, and that parachain invokes a smart contract, which is itself a PVM blob, so we can have all these nested invocations. And finally, PVM has this property where the memory can be dumped and sort of like paused and stored somewhere and then resumed. And this is where CorePlay is intending to use this property. So this pause and resume is also something that is Jam is sort of heavily relying on and wants to implement new things with. And finally, I want to introduce a service that would likely be called Core Chains, or I don't know, Polkadot Parachain service. So one of the first services of Jam will be one that can run parachains. So we can move all the existing parachains into Jam. This would be developed, I think, as soon as some prototype of Jam is ready. Again, emphasizing that Jam is not a disruption or replacement for the Polkadot ecosystem, but rather just a core protocol. Okay, and as a final slide, I want to just leave a few sort of insights and opinions that came to mind while putting these slides together. One is that I think that one of the hardest questions we have now in front of us as a community is figuring out over time what can be best built with Jam as a service, and what should be on top, what should be at a higher level. I think we have a similar dilemma with like what can be a parachain versus what can be a smart contract, and I think we have learned that if you make the wrong choice there, it means you're using a power tool for a tool that is not, for a use case that is not as complicated. And that's generally not a good thing, because then you're sort of paying a lot of cost for benefits that you don't really need. So my understanding so far of Jam services is that they are meant really for low-level things. So it's harder for me to imagine. Like, I'm sure someone will build a meme coin service someday on Jam, that's fine, but I think services are more meant to be modes of execution, operating systems versus applications on top of operating systems. Another interesting insight that I've already alluded to a couple of times is that really, if you look at it at an architectural level, Polkadot has most of Jam within it, excluding things like PVM that are just like, happen to be developed in the last year. Architecturally, Polkadot is Jam. It's just that it's not exposed. So a lot of Jam is already present in Polkadot. I'm emphasizing this mostly to demystify it, to also highlight that if you understand Polkadot, for the most part you understand Jam. It's not like you're starting from scratch. I get asked a lot about service interoperability, and I think up until some point I gave answers that I don't agree with anymore. I think asking the question of how services interoperate with another is actually a bit incorrect question to be asked, because services are not like smart contracts, which have arbitrary entry points that can even be called. Like a service is just two functions. What does it even mean for them to interoperate? It's not like there's a random function you can call into. If they happen to be executed at the same time, their accumulate is called at the same time. I think the question that we should be asking is that the residents of a service, if a service has smaller residents, such as smart contracts, such as parachains, can they interoperate? And this depends on the implementation of the service. The stance that Jam takes here is to be unopinionated and provide flexibility that's needed. Some of you may have already heard about this service that Gav is envisioning, CorePlay. It's a smart contract environment that is meant to be synchronous, so have synchronous composability within its residents. Well, I can go and create, another CorePlay variant that doesn't. So what I'm trying to say is that this interoperability question, it's about residents of a service, not the services themselves. Another point is this term that the gray paper called semi-coherence, in that you have systems that are fully synchronous and are going all in on vertical sharding. Vertical scaling, as in keep the system synchronous, just make it as fast as possible. It's a Solana model. You also had systems that were going all the way on the other end of the spectrum, like Polkadot, or what Ethereum and the rollups are going to be looking like. The system is more scalable, but you have these boundaries and shards, and the system is no longer coherent. It's no longer synchronous. And Jam, with giving you both the in-core computation aspect, which is mostly asynchronous, like what's happening in core, cannot really directly see what's happening on the neighboring core. Jam gives you this asynchronous component and also gives you the synchronous component, which is the accumulate part, the on-chain part, where everything that's happening to one service is visible to other services. So you have both access to this asynchronous part and the synchronous part. So this is why the Gray paper is introducing this term, a semi-coherent system. I think it's literally on the title of the Gray paper. And I really think this is a new big step in the roll-up space. And this is what I mean by I think the rest of the ecosystem is finishing a movie that we've already seen, and we're going to a next chapter. So I think the semi-coherence is also an important part. Okay, I'm kind of over time greatly, so I'm going to wrap it up quickly. And the last point I had is that Jam is a transaction-less chain, meaning that the only transactions that can be submitted to Jam are what we know in Substrate and Polkadot SDK as inherent, as in they are information put there by validators to do work. No user is ever going to transact with Jam. And I'm here to argue that this is great. Actually, this is great because we have this overall criticism in a lot of chains that are kind of like infra chain, that they haven't delivered what they promised or whatever. And I think really one of the problems has been that we have exposed the infrastructure to the end user, as in you're using the same box, developers are using it, end users using it, retail is using it, and I think this is this has been a huge mistake. I mean, it's kind of, in retrospect it's obvious, but I think going forward it's good to correct it. So I think the fact that Jam is acknowledging that, look, I'm a low-level infrastructure blockchain, I'm not for users to come and transact and send DOT tokens on me. That can be done on an application level. I think that's actually a very insightful design choice. Okay, over time, but I'm over, so...
All good.
Yeah.
Thank you, Kian. Stay right here. We do have time for 2 very quick questions or 1 very good question. Who's got it?
Sorry?
Got a question for Kian. Oh, yeah, no, stay right there. I've thrown this far before. Hey, the guy's coming. Okay. Oh. Boom.
Thank you. Is this on?
I have a Q&A section.
Okay.
Hello? Okay. Kian, from your diagram, where does the accords fall in?
Oh.
Can I connect this again?
Can we bring the computer back up here? On screen?
I think in the Jam diagrams we had core as a box. I mean, we can look at it again.
The accords?
Accord.
Yeah.
So accords would now be purely within service. It's not really a Jam concept. It's very much like this interoperability thing that I was talking about. Jam, accords are for parachains to be able to sort of have some shared agreements, accords between one another. This is purely up to this core chain service. It's not a Jam concern. It's not something that Jam, has its specification. It's very much like the interoperability question, as in a service can design to provide something like accords to its residents. That being said, I don't know the reason off the top of my head myself, but I do remember from other presentations from Gav that he mentioned with this design that Jam is bringing, things like Accord, things like XCMP would actually be implementable much easier.
Right.
So.
Thank you.
Awesome. Hey, Kian, thanks very much for coming on.
All right.
We appreciate it. All right, let's give him another hand.